I totally know that the map projection is not really an easy topic that everyone can, absorb and grasp for the first time. So here is my plan for today. My plan for today is I'm going to sing one more time. Okay, so last time I know it was tough. So because I introduced the topic for most of you for the first time, so very, very hard to follow. But today I want you guys right now to lay back, rest as if you listen to a song. Not really the best song, but when I iterate this one more time, I'm hoping it will sound more to your ears. What are we trying to do here in this chapter? Okay, so I will take probably 30 minutes. So last time I spent 2 hours and, we kind of rushed at the very end. I know that very well. And so this time I will try to iterate and do that one more time in a matter of 30 minutes. And to be honest, from my teaching experience, which is so much, okay, I know that when we hear the same thing for another time, things will start to sound right for us. Okay, so let's see. Probably I'll do it one more time and you can give me a feedback on how it looks like after 30 minutes from now. So as we discussed last class, we had a new topic called map projection. And the word map projection has two parts. You can see map, which all of us are aware of what do we mean by map. It's just a graphical representation of the reality. The new word is simply projections. So this is kind of very new for us, at least for now. So the start is here. The start is from something called geodesy, which is a branch of surveying or applied mathematics that focuses on what is the actual shape of the Earth. When it comes to the actual shape of the Earth, here we go. We have three different surfaces and names. And they vary in nature. And I'm going to start with the terrain. So terrain is where you go outside of your house and step. Okay, that's natural terrain. It simply contains, mountains, valleys, ocean beds, and so on. So this is very irregular. The second shape of the Earth is something called the geoid, and the geoid is the gravity field of the Earth, which is the mean sea level and the extension of the mean sea level under the continent. Okay, both of them, they are undulated, they are very irregular. Maybe the geoid is less undulated, but it's still undulated enough not to have a simple equation for it. So finally, scientists, what they said, okay, if we don't have any simple mathematical equation that describes the terrain or the geoid, why don't we come up with our own, created, okay? So the ellipsoid does not exist, created mathematical shape that simply best fit for the Earth. And so the proposal was an ellipsoid. An ellipsoid is very much like a ball. However, it is compressed from the North Pole and the South Pole. I want everyone to remember that ellipsoid is our creature, okay? We created ellipsoid, okay? However, the terrain or the geoid, that's not our creation. And ellipsoid doesn't exist. It only helps us to perform calculations. Okay, next is the ellipsoid. Again, very quickly, the ellipsoid is just a mathematical, shape that, it's a rotation of an ellipse. And again, ellipse is pretty much like a circle while it's compressed from the North Pole and the South Pole. What simply characterize one ellipsoid from another are the size parameters of the ellipsoid. The size parameters here are the semi-major axis and the semi-minor axis given by letter A and letter B. Those are dimensions, and those they characterize the size of the ellipsoid. Now, when it comes to ellipsoid, we had this discussion and we said, oh, we have so many of them. Some of them, they are local. They are a best fit of the Earth in only certain area. For example, one of the best, very famous ellipsoid is NAD 83, as short for North American Datum established in 1983, which is a best fit for North America as the name suggests. And we use it in mapping in Canada and USA and Mexico, three countries. They use the same datum. Other countries, they have another local ellipsoid that is best fit for the terrain in this area. However, when we talk about GPS, and GPS is a global system that allows us to find our location no matter where on the earth. And that's why we cannot deal with local ellipsoid. We need one global ellipsoid that is best fit for the entire globe. Okay, which is we already established that in 1983, and it's called World Geodetic System WGS 84. As I said, how many we have? We have so many. If you are interested, there is one authority here. It's called European Petroleum Survey Group.org. And this authority here, what they do is the archive all the published ellipsoid world wide. So they have a list, and every ellipsoid, it has a name, and it also has a kind of a number in their catalog. Okay, great. We're proceeding. Now, I want to remind everyone, when it comes to coordinate system, we have two kind of coordinate system. The one that you are familiar with, even from mathematics or even first year surveying, is Cartesian coordinate system, which is a set of three-dimensional measurement that characterize the location of the point in space, X, Y, Z, or in surveying called E, N, and H, easting, northing, and elevation. Now, this system doesn't work very well when we talk about the globe itself. So we have another coordinate system that we don't use meters, while in this coordinate system, which called geographic, look at the name, geographic coordinate system, geographic. And in this case, we don't use distance in meter rather than using angles. Those angles are measured in the center of the earth. So the first angle is latitude and longitude. You guys can review what do they mean. All really I want to remind you is they have to be very, very precise. So for example, 1 degree is 111 kilometer on the surface of the earth, because this is an angle at the center of the globe. And remember, our globe, it's a big ball of radius, roughly about 6,370 kilometers. So we have to be very accurate. And you can see, we must say the degree, the minute, the arc second, and even 4 decimal places of the arc second. That's if we want to represent our location to the millimeter level of accuracy. The last dimension, which is called the ellipsoidal height, which is my point. Is it really on the ellipsoid or above or below the ellipsoid? That's the third dimension, and this one is the only one in meters, called orthometric height. I'm sorry, called geodetic height or ellipsoidal height. And we always use a small h for this height, measured above or below the ellipsoid, called the geodetic height or ellipsoidal height. Okay, now, again, talking about height for the same point on the globe, we have two reference datum. We measure the height from the geoid, which is the mean sea level, that is represented in my sketch here with the blue dimension. It is called capital H. This is called orthometric height or geoidal height, because we measure from the geoidal height or orthometric height. The other one in my sketch in green, it's a height from the ellipsoid, which is called geodetic height or ellipsoidal height. We now know that the ellipsoid, it's simply a best fit. So sometimes my geoid is above and sometimes my geoid is below the ellipsoid. And that's why the H capital and H small, they are not the same. And the shift between them, or the difference between them, is called geoid height. We discussed this last time. And what I want you to remember from this class is the conversion between orthometric height and ellipsoidal height is possible, because after we find our ellipsoid, we know the difference between the ellipsoid and the geoid. That's why we're able to convert our geodetic height to our orthometric height. Again, the last information on this slide is GBS does not measure orthometric height, does not. So what GBS measures is the ellipsoidal height above WGS 84 or below. And again, the conversion is possible. There are many software and websites that they can do the conversion for you. Now we have little introduction to geodesy. So map projection. Map projection is a mathematical concept. It's not really originated from surveying. It came from math. It's a mathematical concept, and I give you kind of a analogy where you hold your hand against the light. When you hold your hand against the light, what happens is you will have on some other surfaces you may have a shadow. The shadow is a projection of your hand received on one surface. Okay, so as I said, the problem comes from the fact that our earth is a curved. Okay, our earth is not really a flat sheet. Our earth is a curved surface, while our map, there is no other option. Our map, we plot our map on a piece of paper, and it has to be flat. So the conversion or the projection, okay, I'm going to give you kind of analogy of how it happens. Think about the center of the earth as the light source at the center of the earth. And my point here, my point B here, uppercase B, is exist on the curved surface. And so what we do is we connect by a straight line from the light source or from the center of the earth to the point on the ellipsoid. Then we extend our line until our line hits the map surface. Now, lowercase b is the projection of point B, and ultimately, in map projection, is we try to find a function f1 and f2 that simply take your location on the ellipsoid represented by lat long, and simply shoot on the other side the easting on the northing on the map. Okay, so on the map, because it's a flat sheet, so I can define my x-axis and y-axis, and I can find what lowercase b coordinates in terms of easting and northing. Something that we have already kind of believed in last class is that as we project a curved surface into a flat sheet, so there must be, not a choice, there must be distortion. Distortion. Distortion, it means a change of something. It could be a change of length, it could be a change of area, it could be a change of angle between lines, and so on and so forth. So distortion will happen. As we do the map projection, distortion will happen. We have no choice, because our earth is a curved surface, and you cannot unfold a curved surface into a flat sheet without introducing distortion. Okay, the way we quantify the distortion is by means of something called scale factor K, which is simply a ratio between the length on the ellipsoid divided by the length of the map. And again, I want everyone to remember that scale factor is not scale. The scale is something and a scale factor is something else. A scale is a ratio between the reality and the map, because we don't have a map that has the same size as the reality. While the scale factor, it represents something else, which is the amount of distortion that took place. Okay? Ultimately, your K should be equal to 1. If you can do that, that's fantastic if you can do that. But it will never happen that everywhere on your map, the K will equal to 1. Okay? So the scale factor is not the same as scale. The scale factor will vary on the map. However, the scale itself is constant over the map. So the scale is constant, while the scale factor will change on the map. And again, when K is equal to 1, it means we have no distortion. And then finally, distortion can be minimized, but cannot be eliminated. I need to remind you that those functions are very complicated because we're working on an ellipsoid. So even if we do our best to find a simple mathematical equation, with that even, our math is still very complicated. You are not required to memorize or even understand those functions. Those are developed by crazy mathematicians, okay? And all of them, they are programmed in ArcGIS. And so all you have to do is you need to know how to drive ArcGIS to give you the right answer. Okay, now, as we said, as we produce our map, there is some distortion. So some distortion, it means it will distort your directions, your distances, your area, or your shapes. Maybe you can come up with some projection that maintains one of those properties. However, you will never, that's a fact, huh? You will never find a single projection system that maintains all the aspect of your map. Like, for example, a map that maintains areas and distances and directions undistorted after you do the projection. Really, when it comes to use of map, you can see, maybe you can pick one projection type that maintains your criteria. For example, if you work for the city of Calgary or maybe, Alberta, and then you want to do taxation, then we do taxes based on the area of the land. So we want a map that preserves the area. So when I measure my area from the map, it will give you the true area on the ellipsoid. So this is called equal area map. Okay, but you will never find a single map that fits all the applications. You will never, doesn't exist. Okay, and I'm not going to take you through all of those. Those are different kind of maps, and we already know that whenever we move our, area, different places on the map, what happen is my area will change because of distortion, because distortion will simply somewhere will decrease and some other places it will increase. Okay, now, as a major classification of map projection is simply we can classify based on our map surface. The simplest example is on the left side here, which our map is flat, touching the earth on one point. The other option is we know that we can always fold and unfold a conical into a flat sheet. And also we can always unfold a cylinder into a flat sheet. So one of the other option is something called conical, where you make a cone and this cone is tangent to the ellipsoid at a parallel latitude. Then you do the projection same as we've done before, and then finally you unfold the cone. Remember, in reality, we don't do that. That's only for you to imagine what happens, but the reality is everything turns into equation. So our equation will give us right away the coordinates. We don't really fold or unfold. It's for you to imagine what we're doing here. Same as for the cylinder, we simply wrap our flat sheet into a cylinder, wrap it around the earth, and then do the projection, and then finally unfold our cylinder into a flat sheet again. Okay, now, so this is a classification based on map surface. And I want to show you that we can always do little tweak where we can take one of those, do some alternation, and it will give you a different projection system. For example, for cylindrical projection, this position here of the cylinder where the axis of the rotation of the cylinder is the same as the axis of the rotation of the Earth. So what do we call this one? Normal. So the cylinder here is in the normal position, and this will give me a map. While if I do is same cylinder, no change. All I do is take my cylinder and rotate by 90 degrees. 90 degrees. So this will give us something called the transverse, which means the axis of the cylinder is perpendicular to the axis of the rotation of the Earth. So this will give us something called the transverse cylinder projection. And again, in between normal and the transverse, there is something called the oblique, not very common. But again, it's math. Math has no limits. You can do anything with math. Okay. No, now the most important one, which I want to focus for you and teach you more about, is UTM. So what is UTM? UTM is one of the map projection systems available for us. Why it's very important? Because we can use it to map the entire globe almost. Okay, it is called UTM, as short for universal, because it's worldwide. Transverse, because the cylinder is in the rotated position of 90 degrees. And then finally Mercator, who is the mathematician who invented this projection. So what simply UTM does, it simply uses 60 different cylinders. Okay, not only one cylinder, because we know if you rotate your cylinder by 90 degrees, it will touch your ellipsoid at something called meridian. Okay, and so this meridian, it's called central meridian, at which the scale factor is equal to 1. No distortion, no distortion. And then as you go east and the west of the central meridian, distortion will start to increase. And again, we cannot use one cylinder. Otherwise, distortion will become crazy as we go away from like our central meridian. So how can we solve this puzzle? Is by simply using more than one cylinder. So we do kind of split our Earth into 60 different zones. Why 60? Why 60? Because simply our Earth is 360 degrees in longitude. So if my zone is 6 degrees wide, it means I need 60 different zone. Okay, so every zone is 6 degrees wide, 3 degrees west of the central meridian and 3 degrees east of the central meridian. It means the central meridian is in the middle of the zone. The first zone will start here on the minus 180 or 180 west, and you keep adding 6 degrees. And we looked at what's the situation in Canada. In Canada, it is covered by zones number 7 on the west and all the way to zone number 22 on the east side of Canada. In Alberta here, we have two zones of UTM covers Alberta, which is zone number 11 and zone number 12. In Calgary, we are on the border of zone number 11. And that's why I said last class that Calgary maps has the highest amount of distortion. Now we talked about UTM and we said, okay, so UTM, the zone is 6 degrees wide, 6 degrees wide, okay? And we people created different projection, a kind of alternation of UTM. So some people, they kind of adopt UTM a little bit by changing the zone width. So some, they created another projection called 3TM. So 3TM still transverse Mercator, while the zone width is how many degrees? Only 3. It means 1.5 degree east of the central meridian and 1.5 degrees west of the central meridian. So we have a narrow zone. And for sure, if you follow me, then you would know right away that 3TM has a much better performance in terms of distortion because the zone is narrower than UTM. Now, also people, what they did is they adopted another kind of UTM called 10TM. And I know this is not intuitive because some of you will say 10TM, it has more than the standard 6 degrees of UTM, and it means it has more distortion. Yes, I agree. It has more distortion, but it gives you the advantage of mapping the entire Alberta in one zone. Because if you go by UTM, Alberta will show into two zones, which is 11 and 12. So it means if you want to show Alberta, you must stitch two different zones, and that's not pleasant because you will see some gaps like same as this picture. Or look at this picture here. I'm looking to this picture, huh? If you want to stitch two UTM zones, this is how it looks like. There are some areas where kind of gap that's unpleasant, okay? Now, finally, the last thing I want to mention for you before we ask you about your feedback is in UTM, we simply introduce something called false easting and false northing. Why is that? Because if you look at the UTM after projection, this guy here is one of the UTM zones. Okay, this thing here is one of UTM zones, and the lines that splits this into four quadrant is the equator horizontal and the central meridian in the middle here vertically. And this will tell you, okay, if this is my 0, 0, the origin, it means I will, for some points, I will get negative coordinates for the easting and the northing. To solve this puzzle, very simple math solution is simply adding a constant, okay? So false easting and false northing, those are constants. And what they do is they simply shift everything on the positive side of your coordinate system, and the numbers are there. Again, remember this, false easting and false northing, they have no business with distortion. All they do is avoid the appearance of negative coordinates. And you can see in 25 minutes, I'm able to do it one more time. Show your hands if you enjoyed those 25 minutes and you learned more better than before about the map projection. Okay, thank you so much. I kind of know because again, here's thing for the first time is kind of weird, you kind of shocked. Okay, what's this? But now we kind of sing one more time. Now, I'm gonna spend the next, until the break to show you how do we do that in ArcGIS. And before we start, this is what you need to finish your project. And I encourage all of you to simply after we finished our today's class, please, if you can, this will save you tons of time if you do it later. Today, finish your ArcGIS project. It's going to take you probably from the start to the end, probably 1 hour. But if you do it next week or before the deadline, it will take you forever. Okay, so I'm going to show you right now how simple to do a map projection in ArcMap. We don't have to memorize any of those equations. All we have to do is understand the meaning of map projection and those terminologies that they go with this process. So what I will do right now is I will simply start my ArcMap. Okay, here we go. As usual, when I get the start of my ArcMap, I get my empty project. I can go to my catalog and I already have my folder connection. So my data that I will use is still under GIS-1. So it means I don't have to add any other folder connections, at least for now. I'm going to expand my folder GIS-1, which you guys have it right now. Uh, you know what? What I will do is I will simply use one of data sets under data to merge. So I will expand data to merge. And then you can see, if you remember last class, not last class, the other class, what we did is we looked at merging two different shape files, and I will just simply use one of them. So listen, what I'm going to do right now, I'm going to bring in my only one because I'm not really merging. I'm not merging. I'm just trying to do a map projection. So, okay, so let's try to understand what this file coordinate system is. I want everyone to look at the bottom right corner here, okay? So everyone, where my cursor is right now, please look at the two numbers. And you can see right now it says 109 something minus, which means west, and then 48.5 something, and it's called decimal degrees. Now, this is just a tracker, which means if I move my cursor on the map, those numbers will change. It will follow my cursor and will give me the coordinates. Now, I have a question for you. I want anyone who understands the meaning of coordinate system to tell me, are those Cartesian coordinates or geographic coordinates? Are those Cartesian coordinates or geographic coordinates?
Looks like Cartesian.
Cartesian or Cartesian, those are in meters, okay, are in meters, not in the decimal degrees. Degrees, it means lat long, it means geographic. Okay, so right now my file is in geographic coordinates, which means every point here is represented by pair of coordinates, which is lat long. Lat long. Lat long are angles at the center of the earth, if you cannot remember. Okay, so now let's get more information on the coordinate system. But again, I want everyone to understand that the bottom right corner will kind of give you an idea of what is the coordinate format. So right now, this file it's in geographic coordinates. Again, if you want to get more information about, the coordinate system, all you have to do is move your cursor to the tool space. I'm sorry, I kind of mixed with Civil 3D. It is not called table space, it's called table of content. So mark one of those shape files and then take a right click and go to properties. We're looking at the properties of this shape file. Once you look at the properties of the shape file, this is something we've done before in this class. We looked at the symbology, if you guys remember, to the symbology, and we did some work here, but this time we need to be on the source. Okay, so this window here is very important, and I will show you why it's very important. Number one, do you read the extent of this shape file? Do you read the extent of the shape file? For example, the left side, it's minus 112. So what this number is, this is the longitude of the left side or the west side. West, I would say, don't forget about left and right. It is the west side. So the longitude there is 112 to the west. Okay. How about the right? So the right is 110. And what does it mean? It means we have 2 degrees. Do you see that? So between the left corner or the right edge, we have 2 degrees. Can get some confirmation? Do you see the 2 degrees change in longitude?
Yes.
Okay, so let me ask you, anybody can tell me right away in terms of distance in meters or kilometers, how much is that? If you remember the number that I said last class, every degree in the center of the earth, how much on the earth surface?
111.
111. And you know what? This means my area here is about 222 kilometers. Okay. And then in the north here, there is more than probably about 1 degrees on the north. So this is like 111. So if I cancel this one, it means this area here, it is 222 kilometers this way and 111 kilometers this way. Okay, go back one more time to the properties. Now let's look at uh, the uh, the datum. Is that WGS84 or NAT83? Can you see anywhere on my screen to tell you the ellipsoid name or datum name? Do you see on my screen anywhere that tells you this map, those angles phi and lambda or lat long, are the reference to ellipsoid WGS84 or something else?
North America.
You can see here in the data source, you can see I'm going to mark it for you. The datum is North American datum 1983. Okay, excellent. So, okay, so what is Tahar objective in this class? What is my objective? My objective is to convert this map and do a map projection. A map projection, it means I will take this map and then, for example, put it in UTM. I'm going to show you how simple to do that. Watch me, please. Okay, so I'm going to minimize here. And if you guys remember, we've done this once so far, but I promise you after the break, you will see this is happening so many times. In ArcMap, we use something called the tool. Tool, T-O-O-L, tool. And what tool does, it simply performs one thing for you. So we're doing the projection here through one of ArcMap tools. Where are the tools? How can we get access to them? You guys remember, huh? Maybe it's not really recently, but probably some of you already forgot. We can access the tools through our ARC catalog by going to the toolboxes and then system toolboxes, and here we go. And every toolbox, it has its own toolbox until you go to for example, like this one here, we use it to merge. Okay, I'm gonna expand here. So merge is a tool which is located under general, under data management, and so on. Kind of folder structure thing, huh? Now, we said last class, not last class, 2 classes ago, we said this is insane to get access to our tool through memorization of where is my tool. What is the easier way? What is the alternative to locate my tool? Anyone still remembers?
Search.
Search, exactly. So all you have to do is go to the search, and then you type in the search, you type in the name or the keyword of the tool. Here we go, project. Okay, we're trying to do a projection, and our tool is called project. Okay, so if you search for project, what happens is you're gonna get some results. And since I totally forgot about hitting and be more specific to be click on maps or data or tools, okay, I got many results here. And let me ask you, uh, tell me please, is that the right one, or this one is the right one, or this one is the right one, or this one is the right one? What do you think? Is it number
Data
one or
management.
two, or is it
Data
number one or
management number
three or four?
4.
Number four, huh? Why is that number four? Thank you, sir. It's because you look at the tool here. This is a toolbox. And while we're looking for a tool, so we go here, and obviously this is our tool. And again, it takes some experience, and also the software is giving you some help, because simply it happens under data management. And if you read the description, which happens just below the name, it says projects spatial data from one coordinate system to another. Amazing. Let's go ahead and click on project. So you can see my project tool is here. So simple. I need an input file. I need an output file name. And then let's do it one by one. So you can see here, software is waiting for an input file. Easiest way is I go here, drag this one, place it here. So here is my input file. And what happens here, number one, the software read the coordinate system. You can see it says here North American 1983 CSRS, okay? And then below it offers you an output file name and the location. Would we take this one or change it? Anybody still remembers? Do we take this one or
Change
we
it.
change it? So what we do is very simple. We go here, and then what we do is we say, okay, why don't we say, okay, that is 72E. I'm going to say here project. Okay, so that's the projection of 72E. Okay, and then you can see I'm saving my file here, so it's not on this folder that it's offered from the software. So at least I know where is my file. So under GeoBase data to merge, and it's called 72B project. Then save. Now, what do you think what's missing? Anyone can remembers the idea of map projection? Now I know here is my input file, and here is the name of the output file. Am I missing anything for the software to continue and do it for me? Think about it,
Coordinate
without looking
system.
at my screen. It's the answer is on my screen, but think about it, okay? I'm thinking the software, take this file, change the coordinate system for me, please. And here is the file of the output name of the output file. So what I'm missing, think about it, please. If you think about it, you will see I need to tell the software what is my destination. I'm going from this file here, North American datum CSRS. I want to do to another coordinate system. So what you want to do is define what should be your output coordinate system. Do you guys agree? Show me your hands if you agree. Excellent. So really what you have to do here is that you go to the right side, where you just have to pick what is your output coordinate system. Please watch me. I click here. It opens for me all the options. So what are my options? My options are number one, either stay geographic. Stay geographic, it means I wanna keep my phi lambda, like my latitude, longitude, so I'm not gonna do map projection, and I want to go to a different ellipsoid. I can go from NAT 83 to WGS 84 to any other ellipsoid, so that's also available. But that's not really the topic of our class. Our class, I wanna train you on projection. So I wanna go from a curved surface into a flat sheet. Okay, so you can see here, two options. I can go to geographic or I can go to projected coordinate system. In this class, I will go to projected coordinate system. I asked you, do we have only one kind of projection system or we have many? Watch this. Watch this. You know, ArcGIS comes with so many different projection systems. Okay, we focus on the most important one, which is UTM. So I'm going to ask you guys to go here to UTM. So you expand this UTM. You also need to know what is your ellipsoid. If you cannot remember, I'm going to go back and show you quickly what do I mean here. Okay. So if you remember and focus here. So we said here that map projection, it's simply a function that simply input your geographic coordinates and spits out for you the easting and northing. But also remember, part of the story is A and B. And so can anybody tell me what is A and B? If you remember the discussion, what are those little A and little B? I need one, only one, to make me happy for today.
Semi-major axis. That's
Yeah,
it.
those are, thank you so much. You made my day. Those are the size of your ellipsoid, which means looks like in this step here, I need to tell what is my ellipsoid. So let's say I want to go UTM, I want to go WGS 84, and you can see here what I did is I went to this folder where it simply has all the ellipsoid parameters for WGS 84. And I'm asking you, are we North Hemisphere or Southern Hemisphere? Make me my day, please. And the answer is not very difficult. Is this area North Hemisphere or Southern Hemisphere? Is not very difficult question. Look at the bottom right corner. Look at the bottom right corner and read the numbers, which is we have minus 110 and something. I'm asking you, is this area north of the hemisphere or the southern hemisphere?
North.
North. If you see the latitude here, the 50 with negative, it means that is south of the equator. It means southern. Okay, great. We're very close. So let's go ahead and expand North Hemisphere. Now, what do you see here? Those are the zones. Zones, okay? Like zones. Zones of UTM. And you can see here how many zones. We have many of them. We have total of 60. You can see start here at 1 and it goes all the way to 60 at the very end. Now, this is the next one is not really easy answer. Hopefully, any one of you can do that for me. If you do it, you will make me super happy. Can anybody tell me what is the zone? And I'm going to give you some help, okay? Because I want to help you guys, okay? So, you know, I'm going to show you one picture here on my screen. I'm going to switch back and forth to my GIS, and you tell me, please, what is the zone, the UTM zone. Okay.
11.
Okay, I'll give you one more chance. Okay, so here is this map. I leave it here. I'm going to give you a snap to my software. Take your time, read some numbers here, and then I'm going to take you back to my PDF file, and please tell me what is the zone. I'll do it one more time. So go here, spend few seconds, take one number, huh? You need only one number to know what is the zone. One number only, okay? And if you get this number, great, thank you. Let's look at the map. Anyone to tell me right now, which zone?
11.
Okay, so you know what? I'm happy that you think about it, but it's not right, but I will tell you what's the key, huh? Anyone else wants to try?
12.
12? Hello, is that 12?
60.
Yes.
Okay, guys, it is 12 and I'll tell you how, okay? So anyone can read for me what is the longitude? The longitude right now, it is 110, okay? And remember, if you guys remember, it was between 110 and 112. If you remember, when you look at the extent. So this area is between 110 and 112. Look at the map right now, okay? And remember, those numbers are the border of every zone. Now let me ask you, if your area is between 110 and 112, I'm asking you, which zone one more time?
12.
12. Thank you so much. That's correct, because you can see here, we go here minus 108, 9, 10, 11, 12, 13, 14, okay? 60 degrees. So our area is somewhere here, okay? You guys following? Can I get you to show the hand if you follow? How do we know the zone? You know what? To be honest, I don't know why until now ArcMap does that for us. Because simply it can know based on the numbers on the map, it can identify where is the zone. I myself have developed like a software like back in like 10 years ago, and this software, it will know right away what is the zone number without you telling the zone number. So this is something, to be honest, ArcMap should do it by itself. But anyway, okay, anyway, so again, come here. So really, what you have to do is go to 12. So you need to pick zone number 12. Now, I want you, so now we pick the zone. I want everyone to read those numbers here. Ask yourself, did I learn in entire class what do these names mean? For example, did you learn in my class WGS84? What does it mean? Okay, tell yourself yes or no. Did you learn in my class what does it mean UTM zone 12 north mean? Okay, great. Did you learn in my class what does it mean EPSG? EPSG. This is the authority that simply maintains a catalog of all the published ellipsoid. Okay, now for this ellipsoid, you know what's the number? As I said, it keeps like a serial number for all of them. So this number is called a 32612. Now, did you learn in my class what does it mean transverse Mercator? It's a cylindrical, but the cylinder is rotated by 90 degrees. Did you learn in my class anything about false easting and false northing? False easting and false northing. Why false northing here is 0? Can anybody tell me why here false northing is equal to 0?
Because the northing's already positive.
Exactly. In the North Hemisphere, we don't have to do anything for the northing because everything is positive. Okay. Now, did you learn in my class what is central meridian? The line that splits the zone into two, it's in the middle of the zone. And let's go to the slide. Look at zone number 12. It goes between 108 to 114. And what does it mean? The central meridian here is minus 111. So 111 west of Greenwich meridian. Okay? And this matches what you can read here. Really, really, the one that is, you're going to be mad at me is this number here. Okay? You're going to be mad at me because I kind of deceived you. Okay? If you guys remember the scale factor, it is simply a number that represents the K, huh? The scale factor, it's a number that represents the amount of distortion. And I kind of lied to you. And I didn't lie. Actually, it's kind of half-half. I said on the central meridian, the scale factor is equal to 1. Did I say that? Did I say that the scale factor is equal to 1 at the central meridian? I need some help. Did I say that? Okay, so here we go. I kind of lied and not lied, actually. So yes, theoretically, the distortion is equal to 0. I mean, no distortion on the central meridian, so my key is equal to 1. But what happened is when they developed this system, I'm going to ask you one question, which is kind of, I'm going to leave this first question on the side. I'll ask you one more question, which is now, if distortion is equal to 0.9 and distortion is equal to 1, the distortion factor is equal to 0.9 and distortion factor is equal to 1.1, which one is better, which one is worse, or they are equal? I'll say it one more time. I give you 2 points on my map. where at one point the k is equal to 0.9, another point on the map where the k is equal to 1.1, 0.9 and 1.1. I'm asking you, those points, do you have worse distortion than each other, or do you have the same amount of distortion? Think, please, before you answer, please. 0.9 and 1.1.
0.9, it will be
Equal.
less.
So you think 0.9 has a less distortion than 1.1?
Yes.
Anyone against Kitan?
I
And
think
it's
that's
equal.
correct.
Can you please convince Kitan, like whoever said that they are equal, can you convince in your own language with Kitan why they are equal in distortion? And I agree with this, huh? So you know your answer is correct. In terms of distortion, 0.9 is equal to 1.1. Can you convince Kitan why they are equal in terms of distortion? There is no point better than the other or worse than the other?
If one is the middle, you're equally distorted on either side of it.
Yeah, so one line shrunk after you projected the line and one expanded after, but at the end of the day, you got 10% distortion, 10%, because 0.9 and 1.1, so we have 10% distortion. And that's why, that's the secret why the distortion factor at the central meridian is equal to 0.9996. So whoever invented the system said, okay, why don't we start the distortion at the central meridian of 0.9996? And then as we go away from central meridian, distortion will increase. It will go to 1, and then it will exceed 1. And from the perspective of distortion, to be honest, 0.9 is equal to 1.1. And ultimately, what does it mean? It means when we use distortion factor of 0.9996, we kind of balance distortion on our zone. Balance distortion on our zone. Again, if you get it, great. If you don't get it, that's the best I can do. Okay? Now, what you can do is hit OK, and then finally, we're ready. So hit OK, and then wait. You guys know what's happening right now. My software sending the command to the holy license on state server, and the state server is simply doing the calculation for me. And again, if it's not busy, it will, in few seconds, it will give me on the bottom right corner, it will give me a message and it will tell me, oh, yes, you can see the Nike sign, green. Okay, it means, yes, it has done the projection. Now, watch this. So where is my output file? Now I have done the projection. So I'm going to go back to my catalog, and you will see something that it will simply play with your mind. Okay, it will play with your mind. Watch this. So you guys know where I saved my file, huh? You guys remember I saved my file here. This file is 72e project.shb. So this is the output file. Can anybody tell me this output file, what are the coordinate system? It is going to be UTM zone number 12 WJ84, okay? And this one is projected. It means the coordinate should be in meter. So watch this, please. Watch this. So I'm gonna do something. Again, it's going to play with your mind. I'm going to take this file here, drag it and drop it into my project. Okay? Now everyone, please read the screen. So this is a warning for you. It's not an error, it's a warning. It tells you you are trying to bring in a file that it doesn't have the same coordinate system as the project right now. The project already set up, already based on the first file you drag in. The project coordinate system will be set up based on the first shape file you drag in. I already did. Remember, this one here was the geographic coordinates, and it means the coordinate system right now is geographic. And since you are trying to bring in another shape file that has a different coordinate system, so the software is warning you. And simply, you cannot do anything about it. All you can say is close. And what it does, as the software brings in the new shape file on the fly, and look at the name, on the fly, it simply does the projection. So it takes your projected file and brought it back into curvilinear or geographic coordinates. I know this is too much for you to take, but I mean, watch this. The bottom corner here, it still reads degrees lat long. So some of you may think, I haven't done anything. because simply your software is still reading the latitude, longitude. So watch this. I'm gonna give you something again. Watch this. I'm gonna say close. Close. Is there any close here? Or say new, and then I'm gonna say blank, and I'm gonna save anything. Please watch this, please. As I said, this is very important, very, very important. Now, I will do the input in a reverse way. Right now, I will bring in my projected file first. I will get my projected file first. And here we go. So this was the output of my projection tool, correct? What I will do is, I'm not going to start with this one, 72E. This one is geographic. I will start with this one here. I'm going to bring it in. Please watch the bottom right corner of my screen. Bottom right corner. I'm asking you right now, what do you read? Do you read Cartesian coordinates or do you read geographic coordinates?
Cartesian.
Cartesian, look at this. It's number and it's in meters, okay? Numbers and in meter, which means those are Cartesian coordinates. Now, can anybody tell me what happens if I bring this file here in? Can anybody tell me before I do it? What if I bring this file in now? Second, not first, huh? Nobody knows, huh? Nobody knows. So let's try. So I'm going to bring this one in. You get the same message. It tells you geographic coordinates warning because you initially drag into the project a file that has Cartesian coordinates UTM. Now you try to bring in a geographic coordinates. Do they match? No, they don't. So what happens is, as the software brings in the new shapefile, what it does, it's simply on the fly, it will take your geographic coordinates, put them into project. Basically, it does the same thing I've done in the project tool. I'm not sure if you're following. Is that difficult to follow? Bottom line is the first file, the first shapefile you bring into your project, it will set up the coordinate system. Later on, if you bring another shapefile, has the same coordinate system, great, software doesn't complain. However, if the coordinate system of the new shapefile that you're trying to bring in has different coordinate system, what it does, it will give you a warning, number one. If you say close, on the fly, it will simply do the projection and simply unify the coordinate system. And that's why one of the tricky part, please watch this. And I don't know how I could be more clear on my assignment. So here is my assignment for the GIS project. So here is my GIS project, and I'll show you where in my GIS project I said that. Watch this. I'm going to box it for you. Can you read for me? Anybody can read for me? In a new ArcMap project. So after you do the projection in ArcMap as part of your project, please get a brand new project. And this is now you need to bring in your projected file. Otherwise, if you bring in the projected file into an old GIS project, which already the coordinate system is set up to geographic coordinates, you don't see any change. Is that clear? Can I get your hands if you understand what do I mean? Bottom line is, when you do the projection, after you projected, create a new GIS project and then finish your project. With this, we're done with the GIS project. I mean, we're not done with the GIS part, but we're done with the project. So again, we'll take 10 minutes a break, but remember, today, you should be able to finish 100% of the project. The project has three components. Number one, downloading free data from the internet. Number two, merging the two shape files. Number three, projected the results from the merging process. Very, very simple. If you follow me, you should be able to do it in less than 1 hour from start to the end. And again, there are some other stuff you have to add your name and a skill bar, and this doesn't take any time. It doesn't take any time to add skill bar and skill text and so on and so forth. Do you need a break? I guess you need a break. That's very, very intense session. Thank you so much, and I'll see you in 10 minutes. Okay, so we'll come back here 11:11.